Okay, Year 7s, this is lesson 3 in the dissolving and separating booklet. Here's the question at the top. Does cutting up jelly into smaller pieces make it dissolve more quickly in hot water? Well, what we've got here is a jelly bear, and incidentally, no jelly bears were hurt in the making of this booklet. I just found this picture of a jelly bear online and I cut it and pasted it back, so no one was hurt. We've got a whole jelly cube here, and then it's split into 2 halves, and then we've got another jelly cube that is split into 4 quarters, and then finally we've got a jelly that has been cut into 8 pieces, each of which is 1/8 of the original size. Now, you should be able to understand that this jelly bear here has the same mass as all the others, but this has got a much bigger surface area because it's been cut up into much smaller pieces. Okay, we did this in the last lesson. Prediction. I think that a larger or smaller the jelly pieces are, the quicker or slower they will dissolve. Well, let's have a think about this now. If you put a whole jelly cube in, then the water particles can dissolve it at its surface, but they can't get inside. Whereas if you cut the jelly in half, this surface here and this surface here are new surfaces. They've just been opened up. So now, not only can the water start to dissolve the jelly cube here, it can also start to dissolve these surfaces here as well. So, my suggestion would be that the smaller the jelly pieces are, the quicker they will dissolve, because there is a larger surface area for the water particles to hit the jelly, breaking it up and dissolving the jelly. So, the independent variable here, the dependent and the controls. I'm going to write some answers down here. I wonder if you can't put them into the right place. Before we actually do this, why don't we actually have a look at a video? So, we've got some beakers, measuring cylinders, glass rods, stopwatch and jelly cubes. Let's see what happens next. Oh. We've got one big jelly cube on its own. We've got 2 halves. Then we've got 4 quarters. And finally, the hands are chopping up the 1 jelly cube into 8 eighths. 8 small little bits. Put the jelly cubes into a beaker. Remember, they've got exactly the same mass. It's just that their surface area changes. The smaller the cubes, the bigger the surface area. Oh, we're going to take hot water, pour it into a measuring cylinder. Looks like it's 50 centimeters cubed. Pour the water into the beaker. Start the stopwatch straight away. Start stirring the jelly and water mixture at a steady stirring speed. The jelly is starting to dissolve. The water particles are smacking into the jelly particles, breaking them off, causing the jelly to start to dissolve. And once all the jelly is dissolved, you stop the stopwatch. Okay, we have some variables here. Are they independent, dependent, or control? We have the volume of the water used in centimeters cubed. That was 50. The water temperature, that was boiling water, so that would have been 100 degrees C. We've also got the dissolve time, how long it took for the jelly to dissolve. That's in seconds. We've got the type of jelly that we used. Got to be kept the same, surely. And then the surface area of the jelly, the total surface area in centimeters cubed. Now, we have here the total surface area of the jelly. One whole cube is 15.4 centimeters cubed. The 2 halves, it increases. 4 quarters, it increases. And 8/8 is 30.7. Now, if you want to generate a bar graph, you use this column. But if you want to draw a line graph, use this column. Both of them you're going to use with dissolve time in seconds. Okay, so these are the results that we got. The whole cube dissolved in 0 minutes 41 seconds. Total dissolve time 41 seconds. So, the graph. I'm going to draw the line graph, okay? This is going to be surface area, total surface area in centimeters squared, and this is going to be the dissolve time in seconds. Remember, independent variable goes along the horizontal. Dependent variable, the thing that you measure, goes up the vertical. Now, I'm going to go back to my results table for a second. The biggest surface area was 30.7, so I've got to get up to 30.7. starting at 0. 2, 4, 6, 8, 10, 12, 14. No good. 2s. Going up in 5s. 5s, 10s, 15s, 20s, 25s, 30s, 35s. That does it. And the largest dissolve time, 41. 5, 10, 15, 20, 25, 30. That's no good. 5s are no good. I'm going to go up in 10s. 10, 20, 30, 40. 40 is there. 50. Okay, that's fine. And now I'm going to plot the points. Yeah. So at 15.4, which is there, I'll do this in a different colour. At 15.4, the time was 41 seconds. Right there. And then at 20.5, which is here, the dissolve time was 35 seconds. There's 30, 35 is there. At 25.6 centimeters squared, it was 28. There's 20, 25, 26, 27, 28. That's there. And then 30.7, which is about there. The dissolve time was 22, 21, 22. And then, if I get my ruler, that's quite nice. That's almost a straight line there. So I'm going to take the ruler away. And yeah, that's not too bad. The conclusion. What did you find out? Can we explain why this happens? We've got the jelly cube and the water particles. Think about what holds the jelly particles together in the solid cube. What have the water particles got to do to dissolve the jelly cube? Why did the 4 jelly cubes dissolve more quickly than a big jelly cube, even though the total mass stayed the same? Well, as the jelly cube is cut into smaller blocks, its total surface area increases. So more water particles can hit jelly particles causing them to be knocked off the cube. So dissolving occurs more quickly. So yes, if you were to place, here's another example. If you were to place a sugar cube into hot water and then the same mass of sugar in a, fine grained sugar in a teaspoon, then that teaspoon of granulated sugar would dissolve more quickly. There's more of the sugar is exposed to the water particles coming in and hitting into the sugar particles and breaking them up and causing them to dissolve. Where does all the sugar go? We shall look at that next lesson.